Okay, in this video, as promised, we're going to continue our module 2, and the next new subtopic that you're going to learn is on the IEEE 754. And for this IEEE 754 floating point standard, you're going to have two form of standard. One is your 32-bit and another one is 64 bits. We call as single precision for 32 bits and double precision for our 64 bits. Now, before we go deeper to our single precisions, before we go deeper to the double precisions, let's take a look into our floating point, which we're going to apply later in our IEEE 754. For floating point, computer arithmetic that represent number in which binary form is not fixed. A standard scientific notification for reals in normalized form can be represented in the general form of this one, which is you have -1 as, where s is the sign, multiply with your fraction, multiply with your 2, y is 2, this is a base 2 or binary, and your normalized exponent. This one you already know before this. Okay, in terms of single precision, you know already that it is a 32 bits. For 32 bits, you need to divide into several, similar to your previous format. You got a sign, you got fraction numbers or segmentations, and also a mentesa. And from here you also will got the exponent. For the exponent, now you can see you have a sign, you have exponent, you have also fraction, similar to our previous format, which is your bias exponent format, and also another one is a simple format, a floating representation, right? Now you can see for 32 bits, you're going to have a sign of 1 bit. For 1 bit is a sign. After that, you're going to have 8 bits for your exponent and 23 bits for your fractions. So altogether, when you add 23 add with 8 and also 1, altogether you will get 32 bits. You, as normal format, we will have a range for our standards IEEE 754, and the range is, which is the size of exponent and also our fraction, give MIPS computer arithmetic extraordinary range. So the smallest fraction you're going to have, this is the we can call as a lower bound, your lower bound, and also your upper bound, the smallest numbers that can be supported using these 32 bits or a single precision, and also the largest number, which is a upper bound for our 32-bit IEEE 754. It also can be called as single precision or one word. If you still remember, we have bit, we have also what quotient, not quotient. We have also byte, and we have a word, and yeah, I remember now it is a nibbles. So we have beats, we have nibbles, we have a bite. So for our 32 bits, it's referred to a single precision or one word. So please make sure you remember what is the smallest or the lower bound for your 32 bits MIPS 32 bits, or it called as a single precision number can be supported, and the largest number or the upper bound, which is 2.0 base 10 multiplied with 10 to the power of 38. The lowest will be to the power of 2 2.0 base 10 multiplied with 10 to the power of minus 35. That's the range support for the MIPS 32 bits or single precision. Unfortunately, if you are using a single precision floating point or the 32-bit MIPS 32 bits, you still have a possibility to get the numbers in equations to be too large to support. So let's say you were given with like a very big numbers or very small number, and you cannot have inside this range. It is out of this range. That's why you can also have an overflow or underflow. For overflow, the scenario will be the exponent is too large, or for underflow, the negative exponent is too large. So that's why when we have a problem, whatever in our daily life we have a problem, we're going to find a solution. For this case, what is our solution? One way to reduce this problem need another format that has larger exponent. So we come up with new format called as double precision floating point. Double mean 2 times more better than the single precision. If your single precision is 32, your double will be 64. That's why double precision, also known as two MIPS words, and it will be also 64 bits. And how about the range? If just now you look into your single precision support for the lower bound, 2 base 10 multiplied with 10 to the power of minus 38, and the largest number will be to the power 2 base 10 multiplied with 10 to the power of 38. So please check back for a single precision. Now for 32 bits or the double precision, you will have 2 multiplied with 10 minus 93 98 308, and for the largest number, 10 to the power of 308. So as similar to our format, we should have a sign, we should have exponent, we should also have the fraction or mantissa or significant. So from this you can see sign, how many bits that you have from 64. Going to have only 0 and 1 to represent as a sign. That's why you have only 1 bit for your sign. And then you need to have exponent. What for exponent, you need to check on the equation, of course. And another one is your fraction numbers. So you can see exponent will be 11 bits and fraction is altogether 52 bits. Now you can have over here the IEEE 754 for the standard representation. The standard has greatly improved both the ease of plotting floating point program and quality of computer arithmetic. You can read and go through this. But to pack even more bits into a significant, IEEE 754 make the leading one bit of normalized binary number implicit. So let's say you can have like this one is a single precision or 20. This one is depend on the bits that give in the equation. 0 has no lead to 1. It is given by a reserved component value of 0. What is meaning by this? Let's take a look at an example. Before we go to the example, this is the standard form and the overview how basically the normalization floating point in IEEE look like. It's slightly different with the one that you have currently. S for a plus, E for the normalized exponent. So over here you have IEEE 754 floating point standard for normalized and unnormalized. Before this, if you have the numbers, you need to make it in front as a 0. The rest no have value, which is all 0. And you need to have radix point ataupun nombor perpuluhan. And after this radix point, you need to get non-zero. Whatever number excluding the 0, so then you're going to have the normalized. So from here, let's say we have 103. So you have starting here 1. So it's left to the 1 one time. And now you can see if let's say this one is our previous example, right? You need to have 0 in front, and after your radix point should be non-zero. But when you do for your IEEE, you can see slightly different, which is it's starting with 1. So it's starting with your 1. We have 1.03 times 10 to the power of minus 9. So it's called as normalized. For unnormalized, you can see here we have it's slightly different with our first example. You can see here where I go to the slide. Okay, last time you can see for your normalized, you can see 0 in front. After your radix point will be non-zero. Unnormalized, you have 1 in front. After that is 0. You can have any numbers in front for unnormalized, but as long as after radix point, if it is 0, it's called as unnormalized. But now for under IEEE, that's why I show you the example and also the explanation for these two method, because you're going to apply it in terms of different kind of floating standard. For the single precision, when you have significance equal to 1 plus fraction, what will happen? Okay, now over here, you need to check the normalized and unnormalized. For normalized, you have 1 and after that is 0. Unnormalized, you have 0 in front, after that you have the non-zero. This one, is it normalized or not? It is normalized because after this will be a 0. And lastly, you have 1.234. How to normalize it? You have over here 3. Sorry. Over here is 2, which is it is non-zero. That's why you call as a normalized. Okay, please try to do this example, how these binary numbers can be formed in terms of normalized and also the exponent value. So before we go to the bias notification, we will stop now so that our video is short so then we can repeat several times. Okay, so thank you for watching this video. After this, we're going to directly jump to the bias notification.